Morning, so welcome to the 55th open seminar in Frontier of Nuclear Physics. So this seminar series is organized by the Institute of Modern Physics, the key laboratory of nuclear physics and ion beam application, Fudan University, and the Shanghai Research Center for Theoretical Nuclear Physics, National Science Foundation of China. It is also supported by the programming of introducing talents of discipline to universities, the Journal of Nuclear Science and Technique, and is live streamed on coshare.com. Today, it's our great pleasure to welcome Professor Shinichi Esumi. He is a professor at University of Tsukuba, and he received the PhD from Hiroshima University in 1995. After working at Heidelberg University, he joined Tsukuba since 2000 and took the current professionalship since 2021, serving as the division head for the quark nuclear matter. His primary research field is elementary nuclear physics, including NA44, NA49, ALICE at LHC, Star Phoenix at RHIC, and CBN at FAIR. He has published more than 60 field author papers and hundreds of collaboration papers. Now he is taking on the role of the deputy spokesperson of the STAR experiment. So welcome.
Okay, thank you very much.
Recording in progress.
Thank you very much for the introduction. So I can directly go to the presentation. I would like to talk about the recent result from the beam energy scan program at RHIC. But I would like to include some of other experiments. So I start with some introduction about the experiment and detectors, and then directly go to few related topics, especially concerning on the beam energy scan program. The main focus of the talk is the data coming from the STAR experiment, as you all know, with a few special upgrade for the beam energy scan program, the inner TPC, end gap time of flight, and the event plane detector that I will introduce a little more in the later slide. And I also include some other experiment at SPS and GSI because it is related to the high density area of the physics program too. The purpose of the energy scan is to look for the critical point by scanning the beam energy down to very low colliding energy. The STAR experiment it's designed to measure the collision at RHIC, and the detector is usually used for the collider mode, but we also extend the energy range by having a fixed target and use one of the beam to collide on the target located at the entrance of the TPC, as you see in the top left panel. And this is the three upgrades that I would like to explain. The inner TPC is the same TPC, but only the inner part of the readout chamber is extended to have more granularity, to have a better momentum measurement plus the PID capability, as well as especially measuring a track going out from the end cap. We will be able to catch with the extended granularity inner part of the readout chamber. And we also have end cap time of flight and the event plane detector outside of the TPC to have more capability in the forward region. And you see some of the event display, the collision happening at the entrance of the TPC. And you see on the right-hand side the list of the data we take at the collider mode down to about 7 GeV, and below 7 GeV in center of mass, we can go down to about 3 GeV with the fixed target program. And this is an increased statistics compared to the earlier data set from the beam energy scan 1. We get at least like 10 to 20 a factor of statistics. The particle identification it's done by the TPC and the time of flight, which is almost same as what you do in the RHIC experiment. The specific energy loss and the flight time will give us clear identification of the stable particle, and we need to reconstruct unstable particle by measuring the invariant mass distribution for various different particles, as you see in the slide. The first topics is to know about the temperature of the system by using thermal dilepton mass spectra or direct photon measurement. This is an invariant mass spectra from the dilepton. After subtracting the non-hadronic mass spectra like omega, rho, or phi, as well as psi. After subtracting all these non-hadrons mass distribution, one can extract the excess part of the dilepton spectra. That includes the modified low D distribution, as you see, bump around the low D distribution. And we use this spectra to extract the temperature. And in the lower mass region below 100, below 1 GeV, we see a temperature like 170 MeV, while if you do use upper part of the mass distribution, we get like 300 or more, depending on the beam energy. And we recently extended that measurement down to 7 GeV by including the beam energy scan 2 program. As you see, depending on the beam energy, the shape is similar to the higher energy, but the yield it's getting lower. And this is summarized, the excess in this slide, the excess yield as a function of beam energy shown in the left panel, and temperature shown on the right-hand side. The below 10 GeV, the yield seems to decrease, while depending on the mass range that you try to extract, the temperature is different. If you use lower mass region, it's very close to the phase transition temperature, while if you use up higher intermediate mass region, be between phi and psi, you get like 300 MeV. That can also be seen in the direct photon spectra after subtracting again the hadron contribution plus the QCD prompt photon. So this is extracted direct thermal photon measurement from, this is from Phoenix experiment at 200 J. They also try to extract the temperature at the different PT region. At low PT, they also see somewhat smaller temperature, but at higher PT, they see above 300 MeV. If you use the hadron information, one can try to extract the temperature at the freeze-out. If you use spectral information by doing a blast wave extraction, a model extraction, one can try to see the temperature at just before the freeze-out. That is quite low compared to the previous phase transition temperature. And because we use the spectral, the information, it's we also see the radial flow velocity on the right-hand side, on the x-axis. In the central collision, we expand more, so the temperature tend to decrease even in the central and higher beam energy. While look at in the middle panel, if you use the particle species yield or the ratio, one can try to extract the chemical freezer parameter that is very close to the phase transition temperature, as I also mentioned in the earlier slide. Now, depending on the beam energy, you try to the temperature as a function of baryon density. You clearly see by reducing the beam energy, one can try to go to the higher baryon density. And in our recent measurement at 27 GeV, you see variation as a function of rapidity. The variation as a function of centrality and the rapidity, it's much smaller than the than compared to the beam energy, but you still see depending on the region of the rapidity, we do see a different the chemical potentials that is that is similar to when you vary the beam energy. So if you go to the forward eta or forward rapidity, you increase the baryon density. That is clearly seen in also in the rapidity distribution, as you see in the left-hand side. The proton rapidity distribution changes with the beam energy, especially what is shown on the left-hand side is at 3 GeV, the lowest possible energy at RHIC in star with the fixed target mode to that shows the clear change of the stopping going from peripheral collision to the central collision at this energy. And it is also very much different if you look at proton or light nucleus. If you go to light nucleus, you also see very strong rapidity dependence. The mid rapidity is here. So depending on the particle species, the rapidity distribution, it's quite different. And if you try to do the similar blast wave type fitting at very low beam energy, the dependence of the radial flow and the freeze-out temperature, it's quite different if you do it at 3 GeV. We could also extend this kind of measurement with including the hypernucleus where we can compare to the light nucleus. On the left-hand side, the rapidity distribution of the hypertriton or hyperhelium 4 hydrogen 4 is shown on the left-hand side for the central collision and in the peripheral collision. This also changes quite a lot with the centrality. On the right-hand side, the average PT is shown as a function of mass for the light nucleus compared to the hypernucleus, which does show a similar mass dependence, which could be understood as a coalescence type production mechanism, including hyper and light nucleus. If you look at the energy dependence, the deuteron, triton, and hypertriton are shown with respect to the proton, or as shown on the left-hand side. And the yield increases going towards the lower beam energy. And if you look at the hypertriton yield as a function of beam energy, we seems to have a peak at about the 3 GeV, 3 to 4 GeV, according to our recent measurement of the beam energy scan, including the fixed target mode. If I look at the nuclear modification factor, that is primarily focused for the jet quenching type studies, where if you look at the relative particle yield after normalizing the binary collision, we clearly see a suppression at high PT for high beam energy, while if you go to the lower beam energy, the situation changes a lot, and there is no sign of the suppression at all, which is given by, especially at low PT radial flow, plus the coalescence mechanism that I have also discussed in the earlier slide. And the similar feature is shown if you look at the ratio of the baryon over the meson that is shown on the right-hand side. With decreasing the beam energy, this ratio goes up. And one of the feature that we seen at SPS as a possible indication of the QGP phase transition was this K-pi horn structure at about the 6, 7 or to 8 GeV, where the peak of the K short K over the pi plus is expected according to the high density baryonic matter because of the associated production of the with the lambda, but because of this so sharp structure, we were expecting or imagining this very sharp trend could be a signal of the phase transition that we need to also focus in the beam energy scan to program. Some of the data from STAR and some other data from SPS experiment, and we need to identify if there is really a very sharp structure or not, because the peak structure is expected from the baryon, high baryon density at that beam energy. And the strangeness enhancement was another a possible signature of the QGP at SPS energy that is also seen in the RHIC beam energy scan program. If you look at the ratio baryon, anti-baryon over the baryon with different amount of the quark, strangeness quark, we see quite different ratio. And one more signature that we believe that may be coming from the phase transition at SPS energy was this J-psi suppression at the highest beam energy at SPS, and the typical centrality dependence of this J-psi suppression. And that was also seen at RHIC and LHC, while going up to the higher beam energy, we need to consider about the regeneration at the end of the QGP that seems to increase the yield of the J-psi. So one need to consider both effect of the suppression and the regeneration, especially in case of the J-psi, where we also have new data from the beam energy scan 2 program to confirm the trend of the suppression. And therefore, we need to go to the epsilon to look at the suppression from the color screening, because there are too many charms in the QGP. Therefore, we are not seeing the suppression at high energy. But if you go to the epsilon, we are starting to see the suppression at this LHC energy. And I would like to now move to the anisotropic flow measurement. But this is a measurement at mostly from the STAR experiment, the earlier beam energy scan program. The net proton Boolean slope seems to show quite interesting behavior, where the minimum and the sign change of the Boolean slope, which could be causing the change of the equation step or phase transition. And in order to confirm or test further, we also do this V1 and higher order flow measurement in the beam energy scan. With this new detector installation, where we installed this forward event plane detector, where we measure the charged particle between 2 to 5 in eta, we will be able to really look at the in addition to the improvement of the reaction plane resolution, we could use the same detector to measure the flow of the charged particle in this range to confirm the S-like shape of the charged particle. And with this improved resolution, we also look at the V1 and V3 in the mid rapidity, where we clearly see opposite rapidity dependence, where we see a positive slope in the V1 for the proton and light nucleus, while for the V3 seems to have somewhat opposite trend. One can try to understand the trend by looking at this kind of shape that could be due to the geometry, geometrical anisotropy of the system, plus expansion afterwards. we also try to extend this measurement with the hypernucleus. The V1 slope of the light nucleus compared to the hypernucleus is shown on the left-hand side, which shows similar mass dependence, while there are some small difference that could be due to the strangeness effect. And this measurement has been extended from between 3 and 5 GeV with various different beam energy in the fixed target mode. And that will be extended with the collider mode soon. We also know the V2 has a very typical interesting trend where the sign of the V2 changes with beam energy, as you see on the top left panel, where because of the slow passing time of the two nucleus during the collision and the shadowing effect, we see opposite. A particle can only escape from up and down, which is called squeeze out of the V2. And that is exactly happening at about 3 to 5 GeV, where we are focusing on the fixed target data set, and where the charged particle or proton V2 changes the sign, where we clearly see in the proton to helium-3 V2 measurement at various beam energy. As a function of rapidity, we see a negative slope, negative V2 in the middle rapidity, while if you go to the forward region, it becomes positive. And we usually use this V2 measurement to understand the number of quark scaling. So we try to scale the V2 as a function of PT with the number of quark. That is shown on the right-hand side, where the scaling, number of quark scaling, mostly works at about down to 10 GeV or so. But if you go to few GeV, where you see a breaking of the scaling, that could be understood as the system is no longer partonic, but mostly the hadronic system is formed. And one can also say that this is also a contribution from the spectator or transported quark information into the system. Therefore, if you only look at the negative particle, it looks like it is still holding. We also use the V1 measurement to look for the possible area electric and magnetic field effect we may be seeing, especially if we look at the difference between positive and negative particles, between pi plus, pi minus, k plus, k minus, or proton and antiproton. If you take a difference between the V1 slope, one do see interesting behavior as a function of centrality in each panel and with its different beam energy, with its different color symbol. The slope and even the sign changes. That could be understood as an initial electric and magnetic field affecting to this system. And in the lower panel, the V2, V3 measurement down to around 10 GeV, it's shown as a function of PT. But in this case, V2, V3 are mostly measured with respect to the same order event plane. So the relation to the earlier measurement that I have shown, especially V3 as a function of psi1, it's a kind of very different measurement. So one needs to see the connection from this measurement to the V3 at even lower beam energy with respect to the psi1. We also try to look at the flow in the small system originated from the CMS and LHC PP measurement at high multiplicity, where we seems to see some flow-like effect even in the small system if you select high multiplicity event. That was also done at RHIC and has been also tested with various beam energy, especially for the D-gold collision. That is shown on the left-hand side for the PT dependence and the rapidity dependence of the V2 in the D-gold collision with different beam energy. But in this case, with Phoenix measurement, they are not brave enough to do the non-flow subtraction. So this measurement is purely dominated by the non-flow effect. But in the star experiment, although this is not yet published, but when people try to do the flow subtraction, after the flow subtraction, we do see a clear multiplicity dependence that you may expect. With increasing the multiplicity, we are changing the initial density. Therefore, we may be seeing after the non-flow subtraction, the V2 increases with the multiplicity that may be caused by the initial density, even in the small system. Recently, at RHIC, we also did the oxygen measurement at 200 Jeff in order to compare that with the P-gold, D-gold, and helium gold small system collision to connect the V2 measurement with the heavier system. And this is some of the comparison, again, with or without the non-flow subtraction. So the effect is quite significant in this kind of small system if you do a non-flow subtraction or not. And after the subtraction, one can compare to the different collision system to understand whether the system is indeed flowing or not. And the recent study seems to tell us the oxygen it's somewhat inside structure of the oxygen. It's more like clustering alpha cluster. It's formed, which is it's more than quark subnucleon structure or nucleon structure. In this, if you compare these two, it's more like subnucleon nucleon structure in the nucleus, which is somewhat contradicting to our other measurement, because people were saying it's the subnucleon structure is more important, but now it is not really the case. I find one interesting observation from the CMS in the quark matter that they do this small. It is a small system, but it's a measurement of the shape of the jet, where if you define the jet axis as a beam axis to look at the elliptic shape of the jet cone and to see if the shape is changing with the multiplicity of the jet. No, multiplicity inside the jet, I guess. And that it, if you, especially in the high multiplicity in the jet, you start to see some different shape of the cone, which is similar to the V2 formation in the additional V2 formation in the high multiplicity event, but it may not relate it to the small system flow at all, but it could be related. And I need to go to the high multiplicity, the high density area and the critical point search studies in the next slides. This is femtoscopic type HBT measurement where we show the difference between out and side contribution that we could take it as a duration time of the system, where we seem to see a peak-like structure around 20 to 30 EGB. And if you also look at the sideward radius and longitudinal radius, which is a kind of asymmetric, the size in the transverse compared to the beam direction. Because of the high beam energy at LHC, we are more extended in the longitudinal direction. But if you go to the lower beam energy, it tends to the elongate large more in the transverse direction. And it is changing, going from the beam energy, like this arrow structure. So in the at about few GeV, there seems to be the minimum point in both direction, transverse and in the longitudinal. There may be related to the highest density matter created by the different energy heavy ion collision. And the deuteron coalescence parameter can also be used to guide the volume. This B2 parameter can be understood as a as the inverse of the volume. If the A is 2, that means at this similar beam energy, the volume inverse volume has a minimum, meaning the volume could have a maximum, which can be extracted from the deuteron coalescence parameter, which coincide with its duration time maximum. And one can also try to look at the 3D source geometry by using the HBT type analysis, by looking at the source size from the different orientation with respect to the reaction plane. This measurement is very much typical, that if you look at the source from the in-plane, we see smaller thickness and wide widths. But if you look at the source from the top, the thickness is longer and the width could be shorter. If the fireball at the end of the freeze out, it's still elongated, perpendicular to the event plane. And that is indeed seen in the HBT measurement with respect to the second order event plane, where we still see the shape of the fireball elongated perpendicular to the event plane. And that is decreasing with increasing the beam energy, which is quite similar to the V2 measurement. But this is measurement of the geometry at the end of the freeze out that can be measured with the HBT. And that kind of study can also be used with the first order event plane, where we can see the shape from this side or opposite side of the event plane. And by looking at this as mutual dependence of the source size with respect to the first order event plane, one can try to look at the inclination of the fireball with respect to the beam axis, which is now similar to the Brillouin measurement, because the Brillouin measurement is trying to see the shape, the inclination of the momentum space, but this measures the inclination of the system with respect to the beam axis in the coordinate system, where we see, for example, Nanette proton Brillouin measurement seems to show some negative trend, but it looks like now we are measuring this slope as a function of beam energy, which seems to be always positive. But we are trying to see some possible change in the slope change, in particular beam energy, to look for the small energy dependence more differentially. The few more recent measurement on the baryon correlation, and in the top panel, the proton lambda correlation, and in the lower panel, the deuteron lambda correlation is shown as a function of 3 centrality beam. And this measurement can be used to extract the source geometry for the two system, proton lambda or deuteron lambda. But we also we can also try to extract the interaction parameter like effective range and the scattering length. And it is interesting to see with the deuteron lambda correlation, we could finally separate the spin, two different spin state in terms of the scattering length. We clearly see a difference. And one can also go to the deuteron and proton-deuteron correlation to which now show a negative correlation, where the correlation seems to be repulsive. Maybe because of the baryon conservation effect. And the one of the most promising signal that we believe is to look at the higher order net baryon fluctuation in order to be sensitive to the critical type fluctuation. That it's because we do see, especially for this kurtosis over the skewness, over C2 measurement shows some non-monotonic beam energy dependence in the beam energy scan 2 program. Therefore, now we are trying to increase the statistics with the beam energy scan data set to see if this is really reproduced or not. The two color band that I have drawn, so please don't take it too much because this is my imagination. The blue band is given by the model calculation, including the baryon conservation. That seems to go down with the beam energy. If there is critical behavior expected from the first order, including first order transition and the existence of the critical endpoint, people expect to see wiggling structure with respect to this blue expectation. That's why I just draw a line like this: negative first and positive. With this current beam energy scan one measurement, we cannot say too much with this structure, and therefore we are trying very hard to do the analysis now on the beam energy scan 2 data set that has been taken in the last 2 years, and that could be compared to the deuteron similar measurement from the deuteron or other similar measurement at hardest experiment at GSI. The reason we may not be seeing in the deuteron could just be because of the statistical effect. It's too much because the yield of the deuteron is order of the magnitude small, so the effect maybe a similar effect may be there, but we are not still sensitive with the current statistics, so we need to also increase the statistics. But maybe I could say we could try to even include these 2 measurements to make it more closer to the baryon fluctuation. So we could try to include everything, every possible baryon to do this test. So in the future, I am hoping to include the neutron measurement in the future experiment that I am hoping to do in the next experiment. And it is also interesting to see the recovering of the fluctuation, especially in this wide rapidity acceptance in the hardest experiment, where with going from the peripheral to the central collision, it's not uniform. Uniform dependence. And one of the difficulty that I would like to remind you is the controlling of the volume fluctuation from the initial stage, where even if you do a heavy ion collision, the system has a different size according to the centrality. So we have various different ways to control or suppress the initial fluctuation. The difference is seen as a different color symbol. If you look at this fluctuation as a function of centrality, you do see, depending on the assumption, we see a different result. But luckily, in the central collision, the difference between assumption is small. So one can trust more on the central data set to look at the beam energy dependence. But in the we need to try to make a good control in the centrality analysis on the centrality dependence to really understand the fluctuation. And the acceptance dependence is also a key key part of the study. And if you have a small acceptance, we are anyway limited to the Poisson baseline. That is seen also in this left-hand side, where we increase this is a rapidity cut dependence, but this is trying to increase the acceptance. The left-hand side is the smallest acceptance, and the right-hand side is the acceptance, the largest acceptance possible in the TPC. That is where we see the signature of the fluctuation, which is different from the Poisson baseline. That is what you see in this most right, the red point. That needs to be studied. And if we increase to the infinite acceptance, that is the in case of the net baryon, there should be no fluctuation. So we should be seeing the zero fluctuation again if we have enough acceptance. Therefore, the size of the acceptance is quite important for the net baryon fluctuation study. And we try to go even higher the order fluctuation study up to 5th or 6th order. According to the lattice calculation, the fluctuation could become negative if there is a crossover of phase transition. That seems to be the case if we look at our experimental data. Most of the energy we see slight negative value, especially in the central collision. As you see in the lower panel, this is a multiplicity dependence at one beam energy, and we are seeing slight negative fluctuation for higher order fluctuation. That's why we may be seeing the phase transition could indeed be a crossover according to the lattice expectation. While if you look at the lowest energy point, where we clearly see a very different trend that the value it's positive. So one can also say from this measurement, the system could be very different between the low energy and high energy. Maybe because of the hadronic system or the quark system. That is also clearly demonstrated if you look at the dependence of the order of the fluctuation. So now each panel is the third order, fourth order, fifth order, sixth order, high order fluctuation for different beam energy. And the expectation from the thermodynamics, the most of the calculation expectation goes negative, and the magnitude increases with the order of the fluctuation. And that is indeed seen also in the experimental data between 7 and 200 J. But if you look at the lowest beam energy at 3 GeV, the trend seems to be opposite. So if this is true, the ordering of this fluctuation is given by the thermodynamics. That may mean at the lowest beam energy at 3 GeV is not at all thermalized. But at higher the beam energy above 7 GeV, it could be a thermalized system. And one of the interesting similar observation at about 20 to 30 GeV that we find in this triton production with respect to the proton and deuteron production. If you make a ratio of this triton times proton over the deuteron square, one can think about how neutron is combined into the particle. And if the density fluctuation is large, the triton could be formed more than the deuteron as relatively if you look at this ratio. And that is indeed seen if you make a ratio of this parameter as a function of beam energy. In the peripheral collision, we see some kind of smooth trend as a function of beam energy according to the calculation. But in this, in the central collision, there seems to be some interesting feature that we need also to confirm with the new data set in the future. And I think I am mostly finished. And this is my last topics that we also look at the collectivity in the vertical system, which may also produce some chiral magnetic effect. Therefore, at RHIC we have tried to measure the isobar collision in the last years, and the analysis is mostly completed with its blind analysis technique, and we did see somewhat opposite trend compared to the expectation. That was mostly because of the different structure of the two isobar, and it is below the baseline because of the different effect compared to the expectation. And now, according to the more recent update on the nuclear structure plus the shape of the nucleus and neutron skin and so on, and slight difference between V2 and multiplicity for the same centrality, one can try to draw a more precise baseline to the measurement. That is very much consistent to what we see in the data. So at the moment, there is no hint of the CME signal in the data, but we could at least say the upper limit of the 10% is at the moment. And at the end, I like to discuss a little bit more about vorticity, where we clearly see the vertical structure as a function of beam energy that has been shown earlier. And recently, because if there is a magnetic field effect, one should expect a small difference between lambda and lambda bar in terms of the polarization, where we seem to see some systematic difference between lambda and lambda bar in our earlier measurement. Therefore, we try to improve that measurement with additional event plane accuracy from the event plane detector plus the high statistics data set at 27 GB and 20 GB. But if we try to look at very closely between lambda and lambda bar, we do not really see any significant difference between two. So if you take a difference between lambda and lambda bar, the difference is very close to zero, with respect to our statistical error bar. So at the moment, we do not see any effect from the magnetic field, but the vorticity is mostly coming from the orbital orbital long orbital motion of the system, and the both the polarization measurement has been extended to look at the different direction which could be introduced by the elliptic or triangular flow that is clearly visible according to the psi2 or psi3 measurement that now the polarization along the beam axis with respect which is given by the transverse expansion of the system in elliptic or in the triangular flow, and the global polarization may also introduce the spin alignment that has been recently published and being debated a lot at the moment. So I would decline to comment at the moment of this measurement. And I would like to end my talk with this. Thank you very much. And I spoke too much.
Oh, thank you very much, Shinichi. So this talk contains lots of measurement and lots of information. So we thanks Professor Esumi again, and then I think it is open for discussion now.
Okay.
Wenbing.
Yeah. Thanks for nice talk. This is Wenbing, and I'm a postdoc in UC Berkeley. Could you go to page 20? I have 2 questions. Yeah.
This one, right?
Sorry, I cannot see.
No.
Yeah. First is regarding the VT4 over VT2 ratio, but I don't understand why seems star data prefer the model without subnuclear or without quark degree of freedom. But in the star small system measurement, for example, P gold, D gold, hemisphere gold, you claim you prefer the model with the subnuclear structure.
That's
so,
right.
How do you
Yeah. So it to me it is a little contradicting each other. In the case of P gold, D gold analysis, people say it's more important to include subnuclear structure. But in this measurement, it looks opposite. So I would like to ask more about this, a possible explanation to this. So from this comparison, nucleon is more important than the quark structure, right? So yes, I don't know. I have to ask Shendi or expert on this. Why this is opposite for the oxygen analysis.
Yeah, thank you. And another question at the same page, just the right-hand side, will the stars make a similar measurement and just a VT inside the jet cone as the same as this plot? Will same star do a similar measurement?
I haven't seen any similar measurement in star yet, because this is totally different system, different coordinate system. People define the beam axis along the jet and look at the shape of the jet, whether it's cone, circular cone or elliptic cone. And this tells us elliptic cone is seen in the high multiplicity jet. No, high multiplicity particle in the jet, I guess.
Yeah. So maybe just a related question. May I ask, how do you understand this data? Is it something like QGP droplet or just some other effect?
Yeah, I don't know. First of all, if you believe the non-flow subtraction is important for the small system, one may need to think about such a effect, but I do not even know what to do with this because this is a jet itself. So I don't think, yeah, there may be nothing to subtract to start with.
Yeah, there is two lines from model, just only the non-flow correlation without Lagrange correlation. For example, PCR and Sharper, they describe well at low multiplicity, but at high multiplicity, there is some deviation.
Okay, yeah, that's right. So it's not, it cannot be explained by ordinary effect, I guess.
Okay, thank you. Thank you for a nice talk.
Thank you. May I chat in here? So if I look at, yes, Shinichi, if I look at the Born distribution here, so these model calculation predict the multiplicity, the n-charge distribution from the experiment? Because if I look at the data point here, actually things that there is only the highest multiplicity bin, there is a structure there. So I'm not sure. So if these two calculation describe the n-charge distribution from the data.
So yeah, this is not an n-charge distribution at all, right? This is V2J as a function of n-charge. And you're saying n-charge distribution itself. Yeah, I don't know. Yeah, it could be totally off. Yeah, it could be, I could explain, but I don't know. Do you know?
I don't know. So yeah, just see, because you and women discuss this, and then I want to understand more.
Maybe I should go into more detail of their presentation from CMS. This was shown in Quark Matter, so you could easily find, I guess.
Yeah, okay.
Yeah, I should be talking more about our beam energy scan program.
This is interesting. So let's see if
okay.
Any other question from our student or this audience? Oh, I see Kaija has a question. Do you see the chat window?
Okay, yes, just
thank you very much for the nice talk. Is there any size of change of equation stay in dielectron measurement at BS program?
I don't think we see any sudden change in the measurement. What? I cannot.
Yeah, this is probably in slides.
Maybe onset, but we still we may see some onset at about 7 GeV, where we start to see this enhancement, the typical excess of this dilepton mass spectra start clearly seen at about 20 or 14 GeV. At 7 GeV, the yield gets reduced a lot. So if we take this seriously, the excess is reducing at about 10 GeV. So that may be a change of some system property at that beam energy, but I cannot say more than that from this measurement.
Yeah. Oh, okay. Thank you very much for the explanation. So, do you have dielectron measurements at 3 GeV?
3 GeV?
Yeah,
we are trying, but I haven't seen a result yet. Yes, no, I don't have. We don't have the result yet. Yeah, people are trying to do the measurement, including the fixed target.
Yeah, can we just distinguish? So in the dielectron measurements, how much is coming from QGP phase, and how much is coming from the hadronic phase?
Okay. Yeah. Maybe we could look at the yield. We are using the shape of the distribution to see the temperature, but one could try to look at the yield separately for different mass region. That may tell us something, but I don't know at the moment to answer your correct question. Or you could look at the different temperature depending on the different mass region. If you use the high mass region, one can see this higher temperature, but low mass region, we see this temperature close to the phase transition. So that the merging baryon density or beam energy could be also interesting if you.
Yes, because I think that if, let's say, at 3 GeV there's no QGP phase, then the dielectron, there should be some change in the dielectron measurements.
Okay. So the hardest is here at 2 GeV, 2.5 GeV. So 3 GeV somewhere. Somewhere here, right?
In between. Yeah. So in terms of
excess, it will be somewhere in this region. So.
Okay, I see. Yeah. Okay, thank you very much for the explanation.
Yeah. Thank you. Can you go one more slide? So I also have a similar question. So yeah, here. So do you know if we look at the Phoenix data for the low mass region, the temperature are quite high. If I'm talking about this PT of 1.8 to 1.9 GeV.
1.8 to
0.8 to 1.9. Yeah, it's red point. So the temperature is
it's higher than yes.
The low mass region.
Now, this is the PT space. It's not a mass space, so it may have a different effect. They do in a different PT range to do the extraction, and in the star measurement, it was done in the mass range below.
Yes.
Yeah. So it may have some relation, but it could be different, right?
Okay. Yeah. Now I understand.
Yeah, that could be the reason why they don't go low to below 200 MeV.
Yeah, because this is from non-prompt photon, right?
This is non-prompt. That's right. Yeah.
Okay.
But 1.9 GeV in PT could be still too high.
Okay.
Yeah. I don't know. Yeah.
Okay. And I may ask you one more question. Can you go to the deuteron kurtosis?
Deuteron kurtosis.
Yeah, slide 25.
Yeah, 25. Yes.
Yeah, so the question is that the deuteron kurtosis, so if you look at the left and the right, so the deuteron kurtosis things are different from the proton.
Yeah.
Right.
But if you try to look at difference from the prediction like CE or ULQMD coalescence, it's very close to the expectation. That Yeah, okay. Well, what was the question? I'm sorry.
Yeah, so the deuteron is consistent with the C or transport model calculation.
That's right, yes.
But on the left, the proton,
Yeah.
so I'm talking about the proton. The proton actually has a structure there, right?
Yeah.
So both on central crescent. So how to understand the difference between a proton to deuteron?
This could be because of if the sensitivity is higher for the proton compared to the deuteron, this can happen. The error bar is quite small also for the deuteron, but one needs to look at this kind of plot based on the with respect to the sensitivity of these two measurement. The number of proton is like the order of 40 or
Yes,
at least maybe less depending on the beam energy, but it goes to like at least more than 10. If we take a proton anti-proton difference, net proton. But if you use deuteron, it's the order of few, like 1 or 2. So just because of the statistical fluctuation, one does not have such a sensitivity, especially for the higher order measurement. So yeah, the plot like this, because the error bar is small and the value it's not much difference between the left and right. So it looks like deuteron has a good sensitivity, but we don't see a signal. But it is one needs to look at the one need to imagine the sensitivity of two different measurement that could be very different from the left and right.
Yeah.
So,
okay.
Yeah, but at the end, I cannot promise we see the same thing at the end. So I don't know.
I see. Yeah, I see. Now I got your point. Yeah. So the deuteron actually, each event, the deuteron, the number is very limited.
That's right. And we are looking at the shape of the number distribution. So with its much less number of particles, one cannot really see a very detailed structure of the higher order shape.
Okay. Thank you.
May I have the May I have a question at the same page? Just for the model calculation, QMD plus coordinates. I want to maybe comment that at high energy, for example, at 200 GeV, the QMD not works so well. Maybe there's some QGP phase. So the hybrid model like hydro plus QMD more proper model to describe the high energy neutron productions.
That's right.
So I don't know whether there's some difference in the calculation between hydro plus QMD plus coordinates and compared to the QMD plus coordinates.
I see.
At least I want to at least
But I don't know. I don't know the answer to your specific question. But my guess is there is almost no difference from the ULQMD, usual ULQMD, even if you include the hydro in the high energy. That we need to test in the future. This type of calculation is just used to compare with the data. If to guide the system could be hadronic, or if there is any change from the hadronic system or not. And I agree, if we are sensitive to the partonic stage, we should be seeing the difference at higher beam energy, but because we don't see even from the hadronic calculation. So there may be no sensitivity even if we include the partonic information in the calculation. But that is just my guess. I don't have correct answer at the moment.
Okay. Yeah, I want to say in the nuclear coherence framework, what matters is just the nuclear phase-space distribution.
That's right.
So it's good to check the phase-space distribution of proton and neutron between the model calculation of URQMD and Hydro plus URQMD.
Yeah, that
Okay,
is
that's just a
to
comment.
be compared. Yeah, okay. Thank you.
So just
Okay.
a short question, who did this calculation? URQMD plus correlation. It's from theoretical guys or from
I forgot.
your star group?
Debashish. You know Debashish?
No.
He is from STAR and working on this neutron fluctuation, and from India.
Probably the Vedanga student.
Vedanga student, I guess. Yes. Yeah.
Okay, thank you.
Yeah. Okay. Thank you. So let's see if there's any other question or comments. I see none. I actually have quite a few questions, but things we discuss a lot, so I do not ask. So yeah, it's late, and so I think we are ready to close this seminar. So let's thank again to Professor Esumi again. So for very wonderful talk. Thank you.
Thank you very much. Thank you.
Yeah. Thank you, and thank you all for joining. So this seminar is closed.
Okay.
Okay. Bye bye. Bye bye.
Okay.